Hello students, I am teaching you a course on circuits and system. I am Dr. Ravindranath Rajotia, and in today's lecture we will discuss about the Laplace transform. Well, to begin with, if you remember, in the last class we discussed about the LTI system, wherein we said for an LTI system, if you apply any arbitrary signal xt, then the response of an LTI system was written as ht convolved with the x of t, which was also written as yt equals to integral from minus infinity to plus infinity of, let's say, x of tau h t minus tau and d tau. We also said that this particular equation could also be written as equal to minus of infinity to plus infinity of h tau x of t minus tau and d tau. So this is one of the most important equation for finding out the response of an LTI system. Now we know that the eigenfunction of a system is a signal xt, which when applied to the system produces a response as yt is equal to lambda times of x of t, where this lambda is nothing but the eigenvalues. Also, for a continuous time, the eigenfunction of a continuous time, also the eigenfunction of a continuous time LTI system represented by t. Let's say this is a continuous time LTI system which can be represented by t, are the complex exponentials are the complex exponentials e power of st with s as a complex number, with s as a complex number. That means, that is, if you pass this e power of st to the LTI system, then the response, that is y of t, is equal to a lambda e power of st. So again, this lambda, what you see here, is nothing but the eigenvalues. Now suppose if we let the xt, let me mark with a different color. Now suppose what you have here in the LTI system, I have the LTI system as h of tau x t minus tau. And if you substitute the value e power of st as equal to xt, now let us assume that x of t is equal to e power of st. So putting this value back in equation number 1, and if you put this value in equation 1, then we get then we get then we get y of t is equal to integral of minus infinity to plus infinity, that is this, then h, let me write the integral variable as t instead of tau, it hardly matters. Or for timing, let us assume it is the same, h tau, writing xt as equal to e power of st, then xt minus t will accordingly be e power of s t minus tau and d tau. Now you can separate this e power of s t minus tau in two different components such that you are able to write it as from minus infinity to plus infinity of h tau into e power of minus s tau into d tau as one term, and take e power of st outside this, e power of st outside this. So this will be the solution for it, assuming that if you take xt is equal to e power of st and put it in equation 1. So this means that I now have a term, the integral part, I let it as equal to h of s, some constant value, where s is a complex number, dot e power of st. So these h's are nothing but these h's. So this h's is nothing but your this lambda. So that means I can write this as yt is nothing but delta into e power of st. So what do you have? I can write this as yt as equal to h of s into e power of st, where where this h's where this h's is nothing but the integral from minus infinity to plus infinity of h of tau e power of minus s tau into d tau. So this is where we say this h of s can be written as equal to ht, that is h tau e power of s tau into d tau. So with this equation in mind, so what we can say, does this equation in mind, then we can say, does the eigenvalues of a continuous time LTI system associated with the eigenfunction e power of st is given by hs. So eigenvalues are given by hs. So this means you can say this hs is nothing but lambda s. So this is nothing but lambda into e power of st. The same equation what you have here. So I can say this hs is nothing but lambda. So one thing is this to be remembered. So this above result, that is this particular result, let me mark it with a different color. So this equation underline the definition for the Laplace and the Fourier series. So this is the base for your equations for the Fourier and the Laplace. Now what this s is? This s is nothing but a complex number. So which you can write as a sigma plus j omega. Now with this thing in mind, now we can define your Laplace transform, and with the hs. So we can say this hs is nothing but the impulse response of a continuous time system. So we know that given ht as the impulse response of a continuous time system, then we can say my yt is nothing but the hs into e power of st. So where hs is equal to this part. So the function hs is referred to as a Laplace. So I can now conclude that the function hs the hs is the function hs is referred to as the Laplace transform, as the Laplace transform. Now for a continuous time signal, suppose now if I take for a continuous time signal, if the signal is instead of ht, if the signal is xt, let me again write it with a different color. So if you are given for a signal x of t, then its Laplace will be x of s. What did you say here? For ht, you said it is h of s. If the signal here is x of t, then I will refer to the x of s. And this x of s is nothing but the same equation with the signal as xt. So I can write this as integral from minus infinity to plus infinity of h of t into e power of minus st into dt. So this is my equation for the Laplace transform. And we'll find when you say we are able to drive the Laplace transform x's from the xt, we can do the reverse as well. But in this video, we will complete our discussion with the conclusion that from the time domain, if the signal is time domain, we can find its Laplace, and Laplace converts that into the S-plane. So you get the solution, which is nothing but xs. So thank you for watching. We'll discuss more about in the next lecture.